bit of a trick to this. It's distance divided by time. But let's figure out what went wrong for those of us that did not get this. And I think it probably mostly has to do with the time. Okay? We want to give this answer in miles per hour. The problem specifically says we have to have miles per hour. I saw maybe a few people that had minutes on the bottom. I saw a few people that had minutes on the bottom, which is okay. Your answer could still be sort of correct, but your answer is in miles per minute. And you would need to convert that back to miles per hour before it would be what the question was asking for. I also saw some people with things like this, 6.33 minus 5.22. 6.33 minus 5.22 would give you 11.11. If you do that, 64 divided by 11, or I'm sorry, 1.11 is going to give you 57.657 if you do that. What's wrong with this? 0.33 is not the minutes, because how many minutes are in an hour? 60. So, like, we know, like, if I had given you 6:30, that is 6.5 hours, right? It is not 6.3 hours. So what you have to do for the time there, this is a full hour and 11 minutes, right? If we just sort of count up from 5:22 to 6:22 would be an hour, and then you got 11 more minutes to get to 33. So it's 1 hour and 11 minutes. That is going to be 1 plus 11 over 60. Okay, so that was where we were messing up, I think, the most. And so that the hours should be 1.183 repeating. And then that is going to give you 54.085 miles per hour. Okay, so I think our only issue was just with the minutes. And I did that on purpose just to check with you. It is not really something they're going to do to you on the AP exam. They generally don't, because that's not a calculus topic. They're trying to test if you know the calculus, not whether or not you can convert minutes to hours correctly. So they usually do not do that to you. If they do, they might do like 30 minutes, like they might do half an hour or something there for that. But let's talk about this situation. Jennifer is traveling north on I-77. She passes mile marker 9. Where's she at if she's at mile marker 9? She's in Charlotte. She passes mile marker 73 at 6:33. Where's she at when she's at 73? Getting pretty close to Elkin, right? We got to get like 80, 82 is Jonesville, 83 is your exit over to 21, 85 is Elkin, right? So you're at like, I think 73 is that where you get on like 421? I think it is. I might be off on that one though. But you're getting pretty close to Elkin. Based on what we know about 77, what is the speed limit? 70 for most of it, right? It gets a little bit lower around Statesville, but 70 for most of it there. Why is her speed only 54? Do you think she was going 54 the whole time? She's leaving Charlotte at 5:22. What has happened to her? She has probably sat in traffic in Charlotte, right? Because mile marker 9 at 5:22, especially if it is a weekday, is going to be a nightmare. So, you know, she's broken, doesn't want to get in the express lane. She is sitting in traffic for a while. She probably didn't go 54 miles an hour much at all, right? She was probably going like 10 miles an hour or less for a long stretch. And then she got to 36 and it cleared out and she could drive the speed limit the rest of the way. So average speed was 54, even though she probably wasn't going 54. She definitely went 54 at least one time. That's the intermediate value theorem, right? Speed would be continuous here. You can't go from 0 miles an hour to, 70 miles an hour without crossing 54. So she definitely went that speed at least once, but she probably didn't go that speed very often, right? It was probably traffic. Then she sped up and went to the speed limit. So while this can be helpful for some things, it's not actually the speed limit that she's going most of the time. So average rate of change is just a slope formula, right? We're just finding change in that distance over change in your time right there. But what we're really going to be interested in calculus is instantaneous rate of change, or instantaneous speed. How fast are you going at this point? And I think these problems with speeding, we've already looked at speeding several times, are some of the easiest ways to picture it in real life, because it's such a easy thing to think of average speed on a drive versus the radar gun speed when the cop is going to pull you over. If we look at this, let's look at a different context other than speed. So a function f of t gives the number of students who have voted for homecoming queen as a function of time. Time is measured in hours since 8 a.m. on the day of voting. So what is the average rate of change, f of t, on the interval 0 to 4? Explain this rate of change in context of the situation. So when we see that phrase, average rate of change, we should just be thinking slope. We're thinking slope of f of t between 0 and 4. So they're not asking us for the entire distance here. They're asking us 0 to 4. So we're looking for 0 to 4. So to do slope with those points, we just need to do, we've got the point 0, 35, and we've got the point 4, 256. So we will do 256 minus 35, 5, 4, over 4 minus 0. And so 256 minus 35 is going to be 221 over 4. And if we do 221 divided by 4, we're going to get 55.25. Now, they will ask you for average rate of change on calculus problems, like on the actual AP exam. Average rate of change is really not a calculus topic. You could have done this in Math 1, right? We knew how to find slope. The reason that it is important in calculus is because we need to be able to compare average with instantaneous. And a lot of times they'll ask you to explain in context of the situation. So I've got a number, I've got 55.25. What does it mean? It is votes per hour in this case. Because T is in hours, sometimes it's helpful to label that table right there. And F of T is votes. You could, yeah, I think it would be, it's number of students who have voted, which assuming it's just like 1-to-1, I think it would be okay to say that either way there. So that would be, I think, if you just said votes or if you said number of students who voted, I think you'll be all right in this situation. But when we're talking about averages, we don't have to round because averages aren't real in a way. Like, if we take that every woman in America has an average of 1.7 kids. Nobody has 1.7 kids. You can't have 0.7 of a kid. But whether or not that number is 1.3 or 1.7 matters when you're talking about averages, right? Because that tells, like, that, 1.7 is like, oh, that most families probably have 2, right? That 2 is pretty common. Versus 1.3, we're leaning more towards most families probably have 1 kid. So averages aren't really real. So it is okay to have decimals for them because we're not saying that it is this exact. It is averaging out to be this. So so it would be okay in this case to go with the 0.25. So and what helps me with this is like this is your change in y over your change in x, and so y is votes that goes on top, and x is your t, which is hours. So this is votes per hour. Or number of students who have voted per hour would be even more specific, which could possibly be important if you could vote for more than one person, like if that was the case. So if you're going to explain this, it is very important. You have to give the time frame, right? So the interval is 0 to 4. So from, well, I'm going to actually write it this way. In the first 4 hours of voting, let me make sure. The elementary school, and I think it's just because they had a lockdown drill, but yeah, I don't think I need to actually answer that. I don't know why they call twice. The elementary school calling always makes me a little worried because I'm afraid I've got to go pick up Henry, but especially a lot of times they'll say Amber Jackson on my phone right here, then I know I'm definitely going to have to go get him because she's the nurse. So in the first 4 hours of voting, so somehow you need to tell the time frame where this average is happening. That's what a lot of kids leave off because it's not the entire time that they're voting, it's the first 4 hours. So in the first 4 hours of voting, students vote at an average rate of 55.25 votes per hour. Okay. No, they won't. This, this is math class. You can spell a lot of things wrong. One of the words that ends up on AP questions a lot is vertical, and it can have the word vertical in the problem. Like, find the equation of the vertical asymptote, and the number of children who spell vertical incorrectly with it in the problem is crazy. VERTICLE is the one I saw most often instead of CAL. And it's in the problem. Like, it's there. It's there. And it's still spelled incorrectly. But, if, as long as whatever you wrote vertical doesn't look like horizontal, anything close to vertical, it's just going to be counted as fine. Like, no spelling, no grammar. Now, it is, the way you say things can matter if it changes its meaning mathematically. A couple of you, I have put big circles with a line through it over it that you have used because it is vague, and you need to say, instead of saying it, say what it is, say f of x or f prime of x or whatever you're talking about. So it can matter if it changes the meaning, but if it's just poor grammar, you can get by with it in here. I wouldn't encourage it, but you can get by with it there. So past, present doesn't really matter on this. You could say this some other ways. You could say an average of 55.25 students vote every hour. Each hour, 55.25 students cast their vote. You can word it a lot of different ways. What's really important is the units on this. It needs to have something about votes and hours for it whenever it's in context. There. Okay. And these get asked quite a bit. So it's not even really so much a calculus question. What makes it part of calculus is comparing this to the instantaneous rate of change, which is calculus. There. So average rate of change, you're going to see some, and it's not really calculus, it's just slope for that. So if we look at this question, it gives us a function, and it is asking us the average rate of change of f of x on the interval from -1 to 3. Okay, let's look at this on the Desmos graph, if it'll let me while I'm on it. I'm going to click there. It's just moving it. It's supposed to be a link. It's got the little thing there. Maybe let me copy and paste it. It's not wanting to do that. It's wanting to like run away from it. Alright, let's I'll probably type that one in. It's not too bad. It's like nothing's working like it's supposed to. What is... My computer's about to... Of course it's on a day where half of the people are out, and I really need this recording to work. It won't let me... Let me just get the Desmos pulled up over here. Like this. I'm going to type it in, see if it... That didn't do much, did it? Alright, let's see. We're not going to be able to find that. Alright, well, I'll just have to graph what I was going to look at. Alright, so if I am looking at this graph, and I care about from -1 to 3. So x equals -1 and x equals 3. I'm looking at the average rate of change from here down to here. Right? I'm looking at this point. Is it going to be positive or negative? It's going to be negative because I have decreased during that time. Right? In fact, if I wanted to do y equals ax plus 1 plus 10, put a slider in at a, I can kind of get, right there, somewhere about right here, right? That, we're looking for the slope of that purple line, right there is what we're looking for. That would be our average rate of change for this graph. So let's walk through how we would do that if we didn't have a graph, because something like this is going to show up on Calculator Inactive a lot of times. If we didn't have a graph, what we need for average rate of change is we need the points on the endpoints, right? These right here are both x values, right? Because we're talking about an interval. How do I find the y values for those points if I don't have a graph? Just plug them in, right? So when you do this, cannot stress enough, please label. f of, oh wait, not 0, because we're plugging in negative 1. F of negative 1, so I'm going to have negative 1 minus 2 squared plus 1. That is going to be negative 3 squared plus 1. That is 9 plus 1, which gives you 10. So our x-coordinate is negative 1. My y-coordinate is 10. There's one of my points. And I'm just going to do the same thing for the other. F of 3 is going to be 3 minus 2 squared plus 1. That's going to be 1 squared plus 1, which is just 2. So that second point, x was 3. The y-coordinate that got spit out was 2. Okay, so if I want average rate of change, I just have to do slope formula with those 2 points. So I will do 2 minus 10 over 3 minus negative 1. 2 minus 10 is going to be negative 8. 3 minus negative 1 is like 3 plus 1, which will give us 4. And we get negative 2 for our answer. So if you get this, still just a slope formula. You got to plug in to get those points on your endpoints, but still just a slope formula. But as I have been saying, average rate of change is not really that much of a calculus topic. What we really are interested in is the instantaneous rate of change. So let's see if this one's going to work. So let's look at this beautiful Desmos graph I have made here. And you don't need to worry too much about this over here, but I just want you to admire a little bit my work of setting all this up right here, because I put in all of these formulas so it will show you what I'm trying to demonstrate here. So I have started with the equation of the square root of x plus 7 over x minus 3. Okay, a fairly complicated. And then what we're doing here is I've got these points here. My a could be at any point here. The only point it cannot be at is 3 because the function is discontinuous at 3, in which case nothing exists. But let's say a is right here at 2. Okay? So x, doesn't matter where my x is at. As I take my x and move it over here to my a, that line gets closer and closer and closer to being a tangent line, right? Just touching at one single point, right? And it could also come from the other direction, although it's a little harder to see because it's steeper here. You know, right here, this is a secant line. I'm clearly only touching at 2 points. But, oh, I didn't mean to move my a. I meant to move my x. Well, the x really gets out of hand. It moves quick there. But as the x gets closer and closer and closer to a, my point gets closer and closer and closer to being a tangent line. Right? So, if I'm interested in the rate of change at that point, what I'm interested in is the slope at that point, right? So, if I'm thinking about setting this up, I keep moving my a instead of my x right here. Let's think that x and a are here for right now. If I want to know the average rate of change, I would just do slope formula with those, right? So, if we put this over to the side, come on. There. Oh, wait, that's the wrong one. That's the one we were doing a second ago. That one. All right, if I put this over to the side, then my formula for my slope would be f of x minus f of a all over x minus a. Or you could write it the other way around, f of a minus f of x over a minus x. It wouldn't matter if you switch the order there, but this is more standard to see, so I'm going to write it this way. Here. So right now that just gives me average rate of change. But as x approaches the point that we're looking at, the slope gets closer and closer and closer to the slope of the tangent line, right? So if I want to change this from just being average rate of change to being the actual rate of change at that point, what do I need x to do? Approach a. So if I take this formula and I add the limit as x approaches a, I have the limit definition of a derivative here. A derivative is going to be the slope of your tangent line. It is also your instantaneous rate of change here. Okay, so we can use this. They may use this word derivative, right? A derivative can be defined as the slope of the tangent line that slope of the tangent line could also be defined as the instantaneous rate of change. Okay. Now, this particular version of this only works at a single point. So you have to have a point A that you're interested in. I will show you, it doesn't matter what the equation is. Let me change f of x and I'll make it like something more simple, like x squared plus 3x plus 5. Right? So if I make it something more simple, as x, so right here we're looking at an average rate of change, right? As x approaches a, we get closer and closer and closer to it just being a tangent line there. So whatever that slope is, as it approaches a, is going to give us the slope of that tangent line in this case. So let's use this here. I didn't have a, go back to full screen here. We're going to find the instantaneous rate of change of f of x equals the square root of x plus 1 at t equals 3. Okay? Let's graph it because I think seeing the graph is just helpful for this. So we've got f of x equals square root of, what was it, x plus 1 here. And we're interested in t equals, I shouldn't have used a t right there. I should have called it an x. That x equals 3. So x equals 3. We're talking about this point right here, 3, 2, on the graph. So we're thinking about like what that tangent line would look like. If I do y equals a times x minus 3 plus 2 and put a slider in, like I can mess with that slope till, awful hard to get. That's not exact right there, but I'm getting like close in that case, right? So we're talking about the slope of this graph at that point. So the formula for the limit definition of a derivative, what we just wrote on that last one, is we need to do the limit as x approaches a of f of x minus f of a over x minus a. And in this particular case here, in this particular case, 3 is going to be my A. The point they're asking you for is going to be your A value. So if we plug that in, that means that we need to be doing, I'm going to write over here so I've got plenty of room, limit as x approaches, instead of A, I'm going to put 3. And I'm going to have f of x minus f of 3 all over x minus 3. So you can see right there for those pieces, all those places that had A's, that's where we put this point that we're approaching. So we want to actually figure it out. So we're going to have quite a few more steps depending on the difficulty of the problem here. But now we're just plugging things in. So we're going to have the limit as x approaches 3 of f of x. Instead of writing f of x, I'm going to put what f of x is equal to, which is the square root of x plus 1. And f of 3 means that I should plug 3 into the equation, so square root of 3 plus 1, which will give us the square root of 4, which will just be 2. So we need to have minus 2. And on the bottom we'll have x minus 3. And calculus is so great because it just keeps bringing back stuff we've already done. And we weren't great on this one on the test. What have we got to do to solve this limit? Multiply by the conjugate. So we are multiplying the top by the square root of x plus 1 plus 2, and the bottom, I put that x minus 3 in parentheses, square root of x plus 1 plus 2. So I will distribute here. Square root of x plus 1 times square root of x plus 1 is just x plus 1. And then I've got to do the outer part and the inner part, but those are going to cancel each other out. That's why we chose the conjugate, is so that we wouldn't have to deal with that root anymore. And then negative 2 times positive 2 is going to give me negative 4. Oh, and I'm being lazy. I need to keep my limit notation. And then in the bottom, don't multiply that together. Because you're wanting something to cancel, so you want it to be factored out. Okay. So we're just going to combine the 1 and the 4. That's going to give us x minus 3. So we'll have x minus 3 over x minus 3 times the square root of x plus 1 plus 2. And these will cancel, leaving a 1 on the top there because you have to keep something in the numerator. So at this point, and you want to notice I've kept limit notation this whole time. At this point, we're going to plug in 3 so we can drop limit notation. So once you plug in 3, you don't have to use limit notation anymore. So we're going to have square root of 3 plus 1 plus 2. That's going to be 1 over 2 plus 2. So we get 1/4 for our answer. Here, x plus 1. And if I look at my Desmos graph over here for this, if I go change that A right there, the reason I couldn't get it to work perfectly is because it's going up by tenths, and the answer is 1/4, which is 0.25. If I change that to 0.25, there is my tangent line right there. So the slope of that tangent line's up 1 to the right 4 for that. So that would be the instantaneous rate of change at that point. Okay, so right now, this limit definition of a derivative at a point, that's all we've got whenever it comes to finding instantaneous rate of change or a derivative or slope of a tangent line. That's all we've got, and we've got to do it this way here. So let's look at another one. The position of a particle moving along the x-axis is given by the equation f of x equals x plus 1 squared. What is the velocity of the particle at t equals 1? So if I have a graph, my original graph for f of x, if my original graph gives me position and this is some sort of time. I also used x's and t's interchangeably here. It'd really be better for me to use a t because that probably is time, but I can't change that because it's just the image, so let's just go with x's right here. But x is going to be some sort of time right here, and this is position. Position is a distance, right? It's how far you are away from something. So if I find the slope of this, right, if I find the slope of position, then that's going to be position over time. That's going to be change in distance over change in time, which is velocity for us. So whenever we're given position, the derivative of that is going to be your velocity. So in this case, we could use that limit definition of a velocity, or limit definition of a derivative. So limit as x approaches a of f of x minus f of a all over x minus a. You don't have to write that every time, but I'm going to, so you're remembering what we're doing here. This needs to be memorized. You need to know what that is. Okay, and then what's my a going to be for this problem? 1. So that means I'm going to be doing limit as x approaches 1 of f of x minus f of 1 all over x minus 1. I can live with it if you don't even write that step down. It's okay. But I'm going to make sure we're very clear. So when we start plugging in right here, f of x is x plus 1 squared. F of 1, we can figure out over to the side. Technically, you don't have to. You could do this in your head. But that's going to be 1 plus 1 squared, which is 2 squared, which is 4. So we're going to put a 4 here over x minus 1. So that part is going to get your limit set up for you. Then once you get here, you have to remember how to solve the limit. And that could be any number of strategies that we learned in limits in Unit 1. What should we do for this problem? What do you mean by that? Like, how? Right, we could do that and then multiply those together. So, like, you could do x plus 1, nothing cancels if you do that. You have to, like, go a little bit further. You really want to, like, expand that. I would just double square it here, because when you have a binomial square, you can use that shortcut, but it is doing x plus 1 times x plus 1. So, so that will look like this. Well, leave your limit notation. Don't be lazy. You'll have x squared. Double x times 1 is just 1x. Double it, you get 2x. So x squared plus 2x plus 1 minus 4 over x minus 1. And then if I combine that 1 and that 4, I'm going to get, keep limit notation, limit as x approaches 1 of x squared plus 2x minus 3 over x minus 1. Okay, what next? us factor it. So we'll do the limit as x approaches 1 of x plus 3, x minus 1 over x minus 1. And in these, you pretty much should always have something that'll factor and cancel there. So that cancels, and then we can just plug in our 1. 1 plus 3 equals 4. So we get 4 for that. Okay, question? All right, I've got one more with a few parts that we're going to do here. So same thing. Oh, I think I messed something up here because, oh wait, no, it's telling you what to find right here. So we are given the function f of x equals 1 over x. Here is some new notation for you. It is f with a little tick mark behind it. We are going to read this as f prime is how we would read it. So we're going to say f prime of x. And what it means is the derivative of f. Technically the first derivative, but since we've just learned the word derivative today, you definitely don't know about second derivatives yet. But it means you're just taking like the rate of change one time for that. So we read that as f prime. It means the derivative of f. So this is asking us for derivative of f at -1. So the formula that we're using for all of these is the limit as x approaches a of f of x minus f of a over x minus a. And in this particular case, the a is going to be -1 because that's the number that's inside of that parentheses is the number you're evaluating it at. So we will have the limit as x approaches -1 of f of x minus f of -1 over x minus -1. And f of x is 1 over x. We got minus, we got to do f of -1. What would f of -1 be? If I plug in -1, I got 1 divided by -1, -1. So I got minus -1 over, this is really just like an x plus 1 right here. And, come on. So, really that minus a negative right here also just becomes like a positive, right? What do I need to do to solve this limit? Common denominators. I can't have that complex fraction. So this one is like 1 over 1. It needs to be multiplied by x on top and bottom. So that will look like this. Limit as x approaches -1 of 1 plus x over x divided by x plus 1. Okay, after this, I can flip the second and multiply. So if I put this over 1 right here, I'm going to go around to here. I got the limit as x approaches -1 of 1 plus x over x times 1 over x plus 1. Will anything cancel? It will. 1 plus x and x plus 1 are the same, right? Addition is commutative. I can switch the order on those. So I can cancel these two right here. So now I'm just doing the limit as x approaches negative 1 of 1 over x, which is going to be 1 over negative 1, and I will get negative 1 as my answer. Now this problem is a little bit annoying because now they're asking us to do the same thing again but at another point, right? So it's going to be very similar to what we just did, but I've got to do this again at another point. So it's still going to be the limit as x approaches, but this time it's going to be a positive 1 of f of x minus f of 1 over x minus 1. And that will be the limit as x approaches 1 of f of x is 1 over x. F of 1 is just 1. If we plug in 1, we'd get 1 over 1, which is 1 over x minus 1. Just like the last problem, we're going to put this over 1. We need common denominators, so we multiply by x on top and bottom there. We get the limit as x approaches 1 of 1 minus x over x minus 1. Okay. Dividing fractions, easy as pie. Flip the second and multiply. Now this one's a little harder than the other one because does anything cancel here? Does not. But almost, what can we do so that they will cancel? Factor out a negative for that. So limit as x approaches 1. I'm going to factor the negative out of this first one, so it's going to be negative x minus 1 over x times 1 over x minus 1. And now my x minus 1s can cancel. So I'm going to be doing the limit as x approaches 1 of negative 1 over x, which is going to give me negative 1 over 1, which is also negative 1. Okay. So, pretty similar, but now I've got another one. Okay, I want you to try this one on your own. It's going to be a similar process, but try this one on your own. Your notes are back there with Kindle if you want to grab those. There, so try this one on your own. Okay, so you will be doing the limit as x approaches negative 2 of 1 over x minus negative 1/2, because whenever you plug in negative 2, you're doing 1 divided by negative 2, which gives you negative 1/2, over x minus negative 2. Which both of these double negatives right here just turn into positives. You must get a common denominator here, and since you have different denominators this time, I need to multiply by x on top and bottom for this one, and then I need to multiply by 2 on top and bottom for the first fraction. So in this case, you will end up with the limit as x approaches negative 2 of 2 plus x over 2x over x plus 2. Okay, here, and then this is over 1. And so dividing fractions is easy as pie. We're going to flip the second and multiply. So we got 2 plus x over 2x times 1 over x plus 2. And we can cancel the x plus 2's because 2 plus x is the same as x plus 2. So now we're doing the limit as x approaches negative 2 of 1 over 2x. And that will give us 1 over 2 times negative 2. So we should get negative 1/4 for the answer. Now, I think that we can all agree that that felt kind of repetitive and like you wouldn't feel like doing that if you had to find more points, right? So I partially put this here to lead into something for tomorrow. The definition we're using today is for the limit definition of a derivative at a single point. So you want to know, at negative 2, what was the rate of change? Tomorrow, we're going to see a way that we can do this so that it works for all points, which is going to be helpful if they're asking you for more than one point, right? You don't have to do it over and over and over again. You'll be able to do it a different way. So, limit definition at a point works when you're wanting a single point, but it becomes very repetitive if you need multiple points. So we'll see that tomorrow. Your assignment for tonight, which we still got 15 minutes, so hopefully you can get started on it, is from page 131, 1, 2, 5, 7, and 9. Let me look at it and make sure that is in fact what I want, because I don't think I double checked it. I just copied it from last year. Okay. I do need to note something here. 1 and 2, these are asking you to estimate from the graph. You are not doing limit definition of a derivative at a point here. They did do something a little bit differently on 5, 7, and 9 than what I did in the notes. For 5, 7, and 9, it asks you to find the slope of the tangent line to the graph of the function at the given point. So, slope of the tangent line to the graph at the given point is the derivative. So you're using that limit definition of a derivative. At the point, they're giving you the x and the y coordinate of the point. I only gave you the x coordinate of the point. So they're giving you x and y. You can really just look at the x coordinate. So like whenever you see for number 5, you'll see that they're asking at negative 1, 8. That is at x equals negative 1. It also means that f of negative 1 equals 8. So like when you're setting that up, you'll be doing the limit as x approaches negative 1 of f of x minus f of negative 1 over x minus negative 1 for that. So since they gave you the y coordinate right here, you don't really have to plug it in to find it. But if you do, you'll get 8 and it'll be the same, right? So that's a little bit different than I did in the notes, mostly because a lot of times they don't give you both points, so I need you to be able to do both things. But our book just gives us the x and the y coordinate there, so it's a little bit different. All right, so go ahead and get to work on those. 1 and 2 are just estimating slopes, so you're just looking at like rise over run, estimating those slopes of those lines they've given you. I can. Those are your tangent lines. Those are you're finding the slope of those lines. Yeah. Yes, they're asking you to find both of those. So you got two different. So at the point x1, y1, and at the point x2, y2. So you'll have two separate answers for each one of those. Okay. All right, everybody got what they need here before I cut off the screen?